Hi everyone. Welcome to the ILTA Physics online problem solving lecture. Today we're going to work on some problems related to circular motion. Up until now, we've studied one-dimensional motion along a straight line and two-dimensional projectile motion. But now we're moving on to circular motion in a two-dimensional plane. This refers to motion where the path of a moving object forms a round and round circular shape. Imagine a fly sitting on a spinning turntable, just like in the drawing below. From a bird's eye view, this fly is performing circular motion around the center of rotation. The reason an object moves in a circle like this is because of an acceleration directed toward the center of the circle. The types of problems we'll cover today include basic questions about the period and frequency of circular motion, the centripetal acceleration that makes circular motion possible, and the tangential velocity, which is the actual speed of the object. First, let's briefly summarize the basic theoretical concepts of circular motion. Circular motion is when the path of a moving object creates a circle on a plane. Specifically, we will focus on uniform circular motion where the speed of the moving object remains constant. This diagram shows an object moving in a counterclockwise circular path. When you encounter circular motion problems, three physical quantities should immediately come to mind. First, what keeps the object's path in the shape of a circle is the centripetal acceleration pointing toward the center. At every moment, this center-seeking acceleration constantly changes the direction of the object's motion, causing the path to be a circle. This centripetal acceleration is created by a centripetal force pointing toward the center, following Newton's second law of motion. One interesting thing here is that the actual velocity of an object is always tangent to the circular path, and this velocity is always perpendicular to the direction of the centripetal force or centripetal acceleration. We call this the tangential velocity. For more detailed physical explanations, please refer to my theory lecture first. Now let's look at the quantitative relationships between these physical quantities. First, centripetal acceleration is proportional to the square of the object's velocity and inversely proportional to the radius of the circle. If we multiply the centripetal acceleration by the mass, we can calculate the centripetal force using Newton's law of acceleration. Again, its direction is toward the center of the circle. Concepts we can't miss in circular motion are period and frequency. Circular motion is a type of simple harmonic motion, just like oscillation, and it is the most representative example of periodic motion. The period in circular motion is defined as the time it takes to complete one full trip around the circular path, and the unit is seconds. We define frequency, represented by the letter F, as the reciprocal of the period. Physically, it represents how many revolutions happen in 1 second. The unit is reciprocal seconds, or hertz. Period and frequency have the following relationship with the speed of circular motion. Since velocity is defined as distance traveled divided by time interval, we can calculate the speed of an object in circular motion by dividing the circumference of the circle by the period, which is the time for one full lap. Since frequency is the reciprocal of the period, we can also express the speed of the object using frequency. A moment ago, we said that the centripetal acceleration that enables circular motion is the velocity squared divided by the radius. So if we plug the velocity we just found into the centripetal acceleration formula, we can also write it in terms of period and frequency. All right, let's solve some basic practice problems regarding uniform circular motion together. Problem number 6 is about the motion of a carousel, which we often see at amusement parks. The radius of a carousel is 4 meters, and it completes 0.1 rotations per second. The question asks for the time it takes to complete 2 rotations and its tangential velocity. The first thing to keep in mind is that in many uniform circular motion problems, the velocity conditions are usually given in three forms. It's either given as a period or frequency, the tangential velocity of the object, or the angular velocity, which is a new physical quantity we will learn in the next chapter. Understanding these different ways to express speed is the very first step to solving circular motion problems. In this problem, the speed is given as a frequency. The definition of frequency is exactly what's given, 0.1 rotations per second. Since the period is the reciprocal of the frequency, the time for one rotation is 10 seconds. Therefore, the time for two rotations is 10 times 2, which equals 20 seconds. To find the velocity of the carousel, we can use the definition of speed by dividing the circumference by the period, or by multiplying it by the frequency. For a carousel with a radius of 4 meters and a frequency of 0.1, the velocity is 2.51 meters per second. I hope you clearly understand the concepts of period and frequency in circular motion. Problem number 12 is about a runner on a 400-meter track, specifically their motion during the curved section. A typical 400-meter track has curves at both ends and straightaways in the middle. If the runner completes one full lap in 1 minute and 40 seconds, which is 100 seconds, the problem asks us to find the centripetal acceleration while they are running through the curve. While the overall motion isn't a perfect circle, we can calculate the specific curved part as circular motion. First, let's find the runner's average speed. Since they ran 400 meters in 100 seconds, the average speed is 4 meters per second. Now, the centripetal acceleration when running the curve. The yellow part in the diagram is the velocity squared divided by the radius, according to the formula. By plugging in the given conditions, the centripetal acceleration is 0.43 meters per second squared. The problems we solved today covered the very basics of circular motion: period, frequency, and centripetal acceleration. That's all for today's lecture. Great job, everyone. I'll see you next time.